Okay, this is your Chapter 3 lecture guide to talk about stoichiometry and some chemical reactions. But before we get to that, you can see your table of contents there. For the lecture guide, we're going to talk about moles. We're not talking about a little furry animal that's underground. We're talking about a chemical unit, and it's defined as 6.022 times 10 to the 23rd molecules, atoms, whatever you want to put in that spot. A mole is used to relate atoms or ions. Those numbers of things to a scale that's large enough for us to work with in the laboratory. But a mole, just because it represents a large number, you shouldn't think that it's not an easy enough concept. Just like a mole is a number of things, a dozen is 12 things. So a mole is 6.022 times 10 to the 23rd things, which is represented by Avogadro's number. So how do we know when we have a mole? We could count it out, but who wants to count all the way up to 6.022 times 10 to the 23rd? So more practically speaking, for us in the laboratory, we're going to weigh the sample, get its mass on the balance, and that method would be more preferable. So how do we do that? We need to know the molar mass. Molar mass is the mass in grams, numerically equal to the atomic mass of the element. For example, hydrogen has an atomic weight of 1.00794 grams. That means that mass of hydrogen atoms is equal to Avogadro's number of hydrogen atoms. Magnesium has an atomic weight of 24.3050 grams. So that mass of magnesium atoms represents Avogadro's number of magnesium atoms. And so why the difference in mass? The magnesium atoms weigh more than the hydrogen atoms. So we can calculate things involving moles. And here's a little flow chart. The number of atoms or molecules, if you start with it on that side of the flow chart, you can divide by Avogadro's number and get moles. Then if you want to go all the way to grams, you can multiply by the molar mass of the substance to get grams. Now, if you started at this end with grams, you could divide by the molar mass to get moles, and then multiply by Avogadro's number to get number of atoms or molecules. You don't have to do the whole flow chart. You could just go between grams and moles or atoms and moles, but there is no way to go all the way from grams to moles or molecules or vice versa without going through moles. That brings us to our first example. We want to know how many magnesium atoms are represented 1.67 moles of magnesium. So let's take a look at this, and we want to convert this to number of atoms of magnesium. So we're going to use Avogadro's number, but on the bottom we're going to put 1 mole of magnesium, and on the top we're going to put 6.022 times 10 to the 23rd magnesium atoms. And then we just run that result through our calculator. And we can see our calculator here. And if we type 1.67, we're going to multiply it. And now on this particular calculator, we can type 6.022. And then our exponential is right here. So second E23. And so that'll give us 1.01 times 10 to the 24th magnesium atoms. But that's useful notation here because that E keeps the scientific notation together, which is especially useful if you end up dividing. In this next example, we want to know how many magnesium atoms are present in 73.4 grams of magnesium. Okay, now we want to take this 73.4 grams of magnesium and convert that to moles. So we don't have to use the whole flow chart this time. we're going to use the molar mass of the magnesium from the periodic table, and we'll round to the hundredths place for this, 24.31 grams of magnesium to 1 mole of magnesium. The grams of magnesium are going to cancel, and we're left with 3.02 moles of magnesium, and that would be our answer there. In this example, we want to calculate the number of carbon atoms in 20.0 grams of carbon. Okay, so we want to change 20 grams of carbon, and we're going to figure out how many carbon atoms that represents. So we're going to use the whole flow chart this time. 12.01 grams of carbon to 1 mole of carbon. Grams cancel. Then we're going to use Avogadro's number, 6.022 times 10 to the 23rd carbon atoms per 1 mole of carbon. And then when we run that through our calculator, we get 1.00 times 10 to the 24th carbon atoms. And that would be our answer.